Good afternoon, everyone. We're so happy to have you here, and we're happy to have Matillion here, too, to tell you what they've been up to. So without further ado, please welcome to the stage Ian Fennell.
Great. Thank you very much. Thanks, everybody, for joining. My name's Ian Fennell. I'm the Director of Solution Architecture at Matillion. Matillion is the name of the company, and it's also the name of the product. We have a product called Matillion ETL for Redshift, and also a very similar one, Matillion ETL for Snowflake. It's called ETL. It's actually an ELT product, and there is a very big difference between those two things. I'm not going to go into that in too much detail during this particular presentation. But if you'd like some more information about the differences between those things, then do pop by our booth. It's 1332, which is just literally the other side of that central partition there. So Matillion is all about AWS service integrations, getting the most out of Redshift in particular, but also a number of other services offered by AWS. And I'll be showing some of that during this presentation. Now, if you walk around this expo hall here for longer than 25 seconds, you'll hear somebody telling you that you need to get insights out of your data. And that's pretty much exactly the kind of thing that I'm going to be showing during this presentation. It's not just an idle boast, but actually show you how to do that. I'm going to bring that to life by using seismic data. So switch over here. And this is it's the scientific background to what we're going to talk about, the data set that we're going to use here. So over in the UK, we quite like earthquakes. They're a bit of a novelty for us. They don't happen very often. They're not very severe, so we quite like to study them. I vividly remember the 1989 Great Earthquake, which was it was about as serious as if you bang the table like this, it might cause a few ripples in the drinks. And all over the country, vodka martinis were shaken and not stirred. But that was about the limit of the seriousness of that event. And of course, it's not like that everywhere in the world. A couple of 100 miles west of here, it's a totally different business. It's a very serious threat over there. And there's a very good reason for that. And it's all to do with the plate tectonics, the structure of what goes on beneath the surface of the Earth. So my geologist daughter explains it to me that when two tectonic plates collide, a number of different things can happen. You can, if they hit straight on like this, you can get a mountain range like the Himalayas. They can come to collide and get forced sideways. You get a kind of shear movement like that, and that's what's happening in the North Island and the South Island of New Zealand. They're skidding past each other. Or the third thing, which is called a subduction zone, is what I've got on the screen here. And in this case, the more denser oceanic crust is getting pushed underground underneath the other one, and you get a lot of friction happening there in the actual subduction zone there, and that's where the earthquakes happen. It's very deep beneath the surface, maybe 40, 50, 60 K. So you get deep earthquakes, and that's what we'd like to detect. So they're very big structures, and there should be some kind of a spatial pattern here. That's the insight that we'd like to get out of here. So let's take a look at the raw data for this. This is the raw event seismic data. We're very far from gaining insights at this point. This is what it actually looks like when it comes out of the web service. I've tried to do the zoom in and zoom out a little bit. So over on the right-hand side, you can see maybe 5% of one day's data, and that's what they individually look like. So you can see latitudes and longitudes in here. There's a depth somewhere. It's the -9 in that case. So that's 9 kilometers below the surface. And that data comes out of a web service. It's the latitudes and longitudes that we're specifically interested in here. And you'll notice there's an array right at the top level, this little square bracket. And so that means the entire JSON document with perhaps 200 or 300 events on average per day consists of one giant JSON array. So we have a granularity issue to solve here. This data comes from a web service called EMSC, which is one of those not government or country-specific organizations that exist for data exchange. And that's what I use to get hold of this data. There's a nice web service. You can download a day at a time of data. It comes out like that. So we'll look at the architecture, the AWS services which are going to be used to solve this particular problem. The only thing that isn't within AWS is, of course, the EMSC web service itself over on the left-hand side. I wasn't totally sure where to draw the box for Matillion, so I put it mainly over Redshift there. Actually, Matillion does orchestrate and use all of these services, so you could kind of draw the box right over the whole thing. So we have a Matillion job, for example, that downloads the EMSC data every day and stores it into S3. From S3, that data gets loaded into Athena, and via Athena into Redshift, and it's in Redshift that the data transformations, the aggregations, the spatial functions occur. And with visualizing that in QuickSight, we'll hopefully be able to see some of those patterns, some of those spatial patterns in the data. So let's zoom in a little bit to the way that the data gets from S3 into Athena, and we take advantage of Glue for that purpose. Now, JSON is a really good format for storing data. It's really good for transferring data from place to place in a non-ambiguous way. But it's not so good when you want to interpret that data. You have to do a bit of effort to get the information you need out of there, the latitudes and longitudes, for example, in this particular case. So Glue is a well-named service. It performs the link in between that raw structure and the relationalized data that we need in order to be able to pass that on to a visualization tool. So Glue relationalizes the data. And it does that by crawling your JSON source files. And what I'll do, I'll switch to the next one. You point Glue at the source data, and it comes out with an external table DDL statement, which looks like this scary-looking piece of DDL. Now, if you compare this to the JSON that we had on the screen initially, you would see that it actually does. You've got the array at the very top level there. You've got structures. There's a geometry. It's a named field in there, and that's another structure. So quite a complicated, deeply nested set of data there. You could, if you wanted, create this by hand if you had a lot of time and the motivation to do it. But we figure, let the machine do what the machine's good at, let it parse that JSON and come up with those structures itself. And that leaves us free to work on interpreting and visualizing that data. So you create this external table. Glue and Athena makes that available, ready for use. And the next step is to load that into Redshift. So I'll switch over to here. This is as close as I'm going to come in this short demo to a Matillion, a view of Matillion itself. We do have this available on our booth. If you'd like to see this for real, just pop by the booth. But what I've got is a few screenshots of the different parts of the solution in Matillion. Now, I mentioned at the beginning that Matillion is all about using those AWS services and orchestrating those things. So we've got over on the right-hand side there, the job which transfers data from Athena into Redshift. And it's simply a JDBC load. There's a SQL syntax with an unnest in there, which changes the granularity from 1 record per day to 1 record per event, which is what we need in order to analyze those events individually. At the top there is a drop UDF and a create UDF, and that's a user-defined function. I'm going to come back to that in a few minutes' time, but that's what we'll use to do some spatial processing on the data, specifically to turn those coordinates into something we can use on a flat screen like this. The main thing down the bottom is a transformation job, and that transforms the data inside Redshift. And this is, you can see the ELT pattern happening here. We extract from source, we load into Redshift, and then we do some transformations and get that data ready for visualization. So kind of from left to right along the bottom there, that's the source data, 1 record per seismic event, per earthquake. We invoke the user-defined function in order to convert the coordinates. I'll talk more about that in a moment. There's field splitting, which takes data from pipe delimited varchar fields and turns them into 3 separate fields, for example. Calculations to convert strings into dates. This web service, like many of them, there's the odd duplicate in there. They don't care too much about sending the same record twice in a row, so we don't want to have duplicates in the data, so we take advantage of the Redshift rank function there, which gets rid of duplicates, basically, renaming the columns in the flow. And then there's an aggregation down to a specific spatial grid, which I'll talk about, which is done by the user-defined function. And finally, turning that, getting the average depth within a cell. Because remember, I said right at the beginning, we're looking for the deepest events here, and hopefully we'll be able to see a pattern coming out. So to talk about the user-defined function for a moment, we've got these coordinates, latitudes and longitudes, and they're on a 3-dimensional sphere, basically the surface of the Earth. I want to visualize this on this flat screen here, so I've got to transform those coordinates somehow. And it's like if you peel an orange, you get the peel-off hole, you put it, doesn't sit flat on the table. You've got to flatten it somehow down. And technically, the term for that is a projection. And we're going to take those coordinates and transform them into UTM, Universal Transverse Mercator coordinates, which we can use. They're 2-dimensional, basically. That's a grid that covers the whole Earth. Now, that conversion from lat long into 2-dimensional coordinates is a pretty scary bit of geometry. It gives me cold shivers just thinking about that, but that's what's been encapsulated into the user-defined function there. And the great news is that once that's defined, you only have to do that once, and you can call it from Redshift. So you allow Redshift to actually do that complex calculation over and over again on all of the records of data. So what we're hoping to end up with is that data split into UTM is a 60 by 20 grid, and we'll hope to summarize it up to that level. So the next slide shows you some of the what that data looks like right at the end of the after it's been transformed. So notice, first of all, we've got rid of that JSON. All of that's been parsed out. It's been aggregated up. And a couple of things here which, if we look at this very top one here, that's a grid reference, 31 across. Z is the very top one. There's one event, so there's one earthquake in the 3 years-ish that we have here. It was not that, 10 kilometers, maybe not that deep. So that might be a kind of thing that you would expect for the United Kingdom, for example. Not many earthquakes. The one down here, this one, 33U, a lot of things, 206 they had, very shallow, 3.6K, deep on average in there. That might be typical of Hawaii, for example. Lots of events, pretty small, very near the surface, reflecting the fact that over there, if anybody's seen on the Big Island, the lava coming out, it's a pretty gentle process, actually. There's not too many big earthquakes. So we're beginning to get some insights here. Can't see too many actual spatial patterns. So let's switch over to the visualization. I chose QuickSight, of course, because it's very easy to connect QuickSight up to your Redshift data. And this is the complete data set, and it's just as it comes straight out of QuickSight. So what we've actually got on the screen is per UTM zone. Remember, there are 60 across, 20 on the vertical axis. We have the average latitude and longitude, which gives you the nice grid. If you look, they kind of do line up. It's not perfect, but it works out pretty well, actually. I didn't draw the grid lines on here. So the color of the dots is the average depth, and I've split those into 4 quartiles. So from 1 to 4, the one at the top is the very shallowest, and the one at the bottom is over on the right-hand side there. That's the very deepest ones. So you can see straight away what jumps out of here is, of course, these kind of purple ones, the Pacific Ring of Fire. You've got all of those things, especially down on the South American coast there, up in Alaska, going down the other side of the Pacific, and all around those islands in Indonesia and Java around there. And that's where all of the global subduction zones are occurring. So that just jumps out once you visualize in this way. And we're only able to do this having aggregated that data and turned it into two-dimensional coordinates like this. So you can see straight away, of course, down the places which are very vulnerable to tsunamis and volcanoes, like in Japan, Indonesia. You can see Krakatoa and Tambora over there on the left-hand side, some of the biggest volcanoes in recent memory. So that's the last slide of this. Just to recap, what I've shown is taking that raw JSON data, transforming it in various ways using AWS services, orchestrated by Matillion, in order to get some insight out of here. So we can see some information about the very largest structures on the Earth's surface, those tectonic plates, and it comes out very nicely in the visualization there. So if you'd like some more information about Matillion, hopefully this has given you a bit of inspiration for the kind of things you can do, the kind of things you can use the product for. Like I said, we have two very similar products. The one I showed you was the Redshift product. We also have Matillion ETL for Snowflake. We're available on the AWS Marketplace, and if you launch on the Marketplace, there's a 14-day free trial, so it's a great way to do a POC. Costs you almost nothing. There's also a 72-hour test drive, and the difference between those two things is that for the 72-hour test drive, we host it in our environment, and it just disappears after 72 hours, whereas the ordinary Marketplace image, you own it, it's in your AWS account, you can do whatever you want with it. Also, yeah, of course, if you'd like some more information, visit us at booth 1332. Thank you very much for your time. It's been a pleasure to speak to you. And we'd appreciate it if you'd fill in this session survey in the app. That would be great. Thanks very much.
Thank you, Ian.